Hello, today we're going to discuss about legacy code, and you have a very interesting idea about how to refactor legacy code with pure functions.
Yes, I do.
So let's talk a bit about it.
Yeah, so first I would start from the actual legacy code problem. We have a lot of customers who come to us complaining about legacy code, and the typical problem is we've written a lot of code for many years, and while developing, the development speed has gotten really down because now we don't understand anymore what's in the existing code. And we often see that it's very hard for people to get into code and actually change something there because they are very afraid not to break something else. Yeah, and I think usually this happens due to past bad experiences. So you change something and then you get a lot of complaints from a completely different area of the code, and then you don't want to change code anymore. It's just a big no-no.
Yeah, and probably you're very afraid to do everything there, or there are areas where it's difficult to change code, right?
Yeah, I mean, there are a few. Usually there are, even when you are trying to write code that's very clean and very neat and so on, there are areas where you kind of push forward and you need to deliver fast, and then you don't have time to go back and clean things up, and after 2-3 years nobody knows what's there anymore. So
yeah, but there are areas where you can have code that's nicer and code that's not that nice and code where nobody touches. So let's say that we want to focus with these legacy code techniques on the very nasty code, right?
Yeah. And I think this is the thing that I was looking for. I was looking for a method that could help developers actually start changing code in areas that are very difficult to understand, very difficult to change, where we are very afraid to go and change things, but do it in not only in a safe manner but also faster than with what we have as techniques.
So the idea is that we want to make the programmers feel a bit safer and being able to push a bit, maybe step by step, not make big changes necessarily, but be showing that they can be confident with these things.
Yes, and part of it is practice, part of it is technique, but it's part of it is knowing how to deal with this kind of code structures that are not very clear, where the code is quite difficult to understand. Yeah, so. And we know that there is, let's say, a standard method for dealing with legacy code.
Yeah, like the Michael Feathers book.
Yeah, the Michael Feathers book, which if you haven't read, you should read it. It's a really, really good book about how to deal with it. Now, it's interesting to me, as an aside, that often when programmers complain about problems with legacy code, managers tend to see it kind of like that's your job.
Yeah, do it.
You just do it, you just change existing code. Of course, that's what the programmer does. Unfortunately, that's not as simple as it looks, because there are degrees of how easily you can change code. If you understand the code, if you've just written it, if you have it very clear in your mind, then it's easy to change. But if it's something that maybe a colleague wrote 10 years ago and he left the company and everybody else who ever touched the code has left the company, then good luck with that. It doesn't work. Right, so then Michael Feathers came up with this brilliant idea of a method for dealing with legacy code, and it basically goes like this. First, we break dependencies, and we use there are probably 15-20 techniques for breaking dependencies, more or less.
A few are very well known and used, but maybe 3-4, but there are many more.
Yeah. And yeah, and for example, one of them is extract and override. That's a very common one. Strangler pattern. So there are a lot of dependency breaking techniques, and the goal of these dependency breaking techniques is to allow you to write tests that characterize the current behavior of the system.
So there are kind of tests that aren't necessarily unit or system or component. They can be anything, but they need to characterize. So we write code, a test on existing code.
Yes. So imagine that you have no idea what's in that code. You try to read it, but you don't understand it.
And even if you understand it, you might not really understand what it does, and that may be, well, not that good.
Yeah, and often what we notice is actually it takes even longer to try to read and understand code than to kind of play with it. And in my mind, whenever I write characterization tests, what they help me with is kind of learn more about the system by playing with it, exercising it. And so examples of characterization tests will be if I see a function that has two integer parameters, I would pass in, for example, for 0 and 0, and then 0 and 1, and then 0 and maximum int, and then minimum int, and 0.
And see what happens.
And just see what happens, and just document what's happening. So my tests will just say, okay, so if you pass 0 and 0, this returns 5. I have no idea why. I don't know how to name this behavior, but I kind of document what's going on there.
And then we keep this like a safety net for the future changes that will lead to the code.
Yeah, so, and that's the main thing, because often there's a tendency of programmers to jump into the code, kind of start changing it and so on, and maybe try to debug it. Now, the problem with this is if you don't know exactly how it should behave and you start changing it, the risk is that you'll end up with something that doesn't behave properly anymore.
And even if you wrote it yourself, it's very probable that after 6 months you don't know what it does. So if it's written badly, or if you just wrote it fast, in a hurry, sloppy, it's difficult.
Yeah, I have code that I even give some examples of some code that we actually use in Mozaic Works right now. It works, but when I look at it, I have no idea how it works anymore. So because
it's normal,
I did a few experiments with that code, and it's very weird now. So it happens to everybody. It's not something that we see only in with our customers. It happens even to people who actually try to write very clean code. It's so that's why you need the characterization test, so that when you refactor, it actually allows you to be sure that you haven't broken anything, or at least be more certain that you haven't broken anything.
Yeah. And you need to add enough tests. You don't know necessarily how many, but you need to add enough tests to be kind of sure that you can go on.
Yeah, and then if we go back, the reason you cannot start with writing the tests is that usually you need to write your tests on some code that's deep inside the system, on some class that depends on 20 different classes, maybe on a logger, maybe on a timer, maybe on system time, maybe on file system, and so on. And you often see that this code is kind of bundled together. So maybe you have a large function that just uses system time, writes and reads from file system, and calls 10 other classes and so on. And if you want to write tests on such a class, it's very difficult unless you kind of start to break the dependencies a little. And of course, that's where the breaking dependencies techniques.
Yeah, so dependencies means basically anything that's difficult to test, anything that's big, like an external system, maybe file system, maybe a database, maybe other systems. So this is what dependencies mean, because it's very difficult to set up a machine with all of that things just for you to make sure that you could test everything integrated and have this as a safety net. So that's why we prefer to break dependencies and be able to test in memory whatever we have, right?
Yeah. But also you don't want to change too much, because you don't want to change the behavior too much, especially for code that you have no idea how it works or what it's supposed to do.
Exactly, yeah.
So that's the fundamental basic technique. Now, we've used this technique for many years. And one thing that I noticed is it's very slow. The challenge, even if you have a lot of skill, even if you know all the techniques, even if you've practiced each of the breaking dependency techniques, even if you have a really good way of writing tests, it still takes a long time, because usually legacy code by definition is some code that you don't understand, that has everything kind of bundled together in one thing. And to me, I think that the fundamental difficulty to refactoring legacy code actually is in the dependencies. And it's actually in the fact that whenever you want to write tests and to refactor, you need to figure out, okay, this line of code actually depends on 20 different other things that need to be in a specific state, or and so on. And when I started looking at functional programming a few years ago, to learn more about functional programming constructs and how design changes when you use functional programming constructs, it turned to me that functional programming has a really nice feature. It's the construct called pure functions.
And that comes basically from mathematics, saying that you have pure and impure functions, right? So let's see about that a bit. How we define that?
Yeah, so well, a pure function is a function that returns the same result when it receives the same values as parameters. That's basically it. So you can think about a pure function in a different way. You can think it as like a very big table of data, where you have all the possible inputs in columns, as many as the number of parameters, and then you have all the results. And a pure function is equivalent with this table. It's kind of the same thing, right? And the really good thing about pure functions is that they are very boring, right? You can look at a pure function, you know exactly what it will do. You can test it easily. You can write a big table that says, for these inputs, I expect this output.
And maybe the reason is also that because you need to use all the inputs, you cannot have it very big, right?
Yeah.
You cannot have a very big pure function, only if you have a very complex algorithm.
Yeah. So that's usually where you end up, although we'll see in that when refactoring legacy code, you can actually go through very large pure functions, but it's still good to have them. So now another, by definition, an interesting property of a pure function is that it doesn't have dependencies.
Exactly, because those functions that have dependencies are impure, so they touch external parts of the system. They touch, I don't know, memory or other things around. You cannot even declare anything in a pure function, so everything needs to come from outside as parameters.
Yeah, I mean, you could have local variables. Here it's a long discussion.
It's a long discussion between functional and...
It depends how purist you want to be. It's because by definition, the only constraint is that it returns the same outputs when it receives the same values as inputs. Whether you have internal variables or not, and other things.
So in functional programming, we want to separate state from logic. So that means that you put a bit of state where you have logic, so it becomes impure.
Yeah. But
for us, it's not that important.
For us, it's not that important, and for our goals. So that can be a very long discussion, but we don't have to go into it. And also I realized another thing. Whenever we do data transformation, so kind of a side idea, whenever we transform data from, let's say, we receive some CSV and we want to turn it into, I don't know, PDF or XML, or usually every such data transformation is done through a nominal format. So you first go through a nominal format and then you move to the output. And the reason for this is that it's usually easier and it's more, you can implement more such, it's reusable, right? So you can implement more types of inputs, more types of outputs, as long as you have something in the middle that's similar, that's nominal or standard. And what I would argue is that so a program that has in the middle pure functions and around the pure functions has the input-output stuff, that for me is a nominal format for design.
Okay.
Right? And this doesn't mean that this is how every program should be constructed. It just means that you can write every program like this. And that's an interesting property, right? So then the idea that I had was, what about taking advantage of pure functions and changing a bit our legacy code refactoring so that we split it into a few steps. First, we refactor to pure functions. Then, because the pure functions are very boring, you can easily test them, right? And you can write here data-driven tests or property-based tests.
Which are a bit faster to write, in fact.
Yeah, and they are quite easy to write. You can use data generators, you can use a lot of cool things there. And then once we've done this, then you can refactor your pure functions into whatever you want. So you can make them more pure if you don't like how they are. You can make them smaller if they are too big. You can group them into classes and then go into object-oriented design. And this is a method that I experimented with. And it was very interesting to see that I could refactor to pure function in a purely mechanical way without running any tests. And after I'd done that, the code still worked perfectly. Now, how did I know? Because I had some tests in the beginning. Yeah.
So how do you do that? What's the mechanism? What are the mechanics of doing this?
Yeah, so there's a simple mechanics that I used again and again, and it takes into account the fact that pure functions are actually fractal. So you can start, let's imagine you have a class, you have a big method inside that class, you want to refactor that class somehow, right? You can start at the method level, or you can just pick code, a set of a group of lines of code from that method. For example, something that's inside of an if-else statement, something that's inside a for loop, or something like this. Or even just 2, 3, 4, 10 lines. It doesn't matter. So you can start from any level, and then just extract that as a function. You can use your IDE usually to do that. So extract a normal method out of those lines of code. That's the first step. The second step is to make it static. And this is actually a method that I learned during one of the legacy code retreats that with Eric Talboom. So it was quite interesting to see there that it was very fast to identify dependencies. Because once you make it static, the compiler will tell you all the dependencies this function has.
And then you can, it will tell you this is wrong, you need this or that. Or even if you make it static and something goes wrong, you can see it. So
yeah.
Immediately you can even run it and see if something works or not. And also it's very interesting that it shows you very fast. So if you use an ID and you extract it, you'll see immediately, oh, I need this. So you don't need to try and reason what to use, what parameters need to be used, and so on. So that's very interesting because it helps a lot.
Yeah, so that's one of the points related to efficiency, right? So instead of me thinking what code, what are the dependencies, how should I break them, where are they, and so on, I let the compiler tell me. And the compiler just tells me, oh, I'm missing this, and these things. And then the interesting part comes from another thing that's now possible in all mainstream programming languages, which is you can actually extract the part of code that contains the dependency in a separate function and inject that function
so
as a lambda.
Go towards functional programming even more.
Yeah.
And we start using functional constructs in this type of refactoring.
Yeah. And so then what you end up with, it can be quite a big lambda, let's say, a big pure function that has a lot of parameters. Some of them are data parameters, some of them are other lambdas that are injected. But the nice thing about this is that without even realizing, you extract the dependencies, right?
And it's refactoring because you don't change any part of the structure. So you just refactor from the existing functions to lambdas and maybe high order functions, right?
Yeah. And once I do that, so if you do this until your function becomes completely static, then you still need to pay attention to a few things. There's another situation when you have a change in state inside the function, right? And that's where you need to apply another type of refactoring where you basically store the initial value, you receive it, you have a function that returns the new value, and you store it again, and so on.
So again, not very pure functions because you have state, but it's fine.
Yeah.
It's needed.
Yeah. So yeah, we are starting from an impure world, so that's why we need to blend it a bit and go step by step. But the nice thing is once you apply these steps, you end up with one function that is pure, with a number of other functions that surround it that are injected, that are also pure, because you also try to make those static and kind of do the same process for all of them. And this is just by using the compiler and using your refactoring tools from your IDE or just manual refactorings if you know how to do them properly.
So that's a lot faster. That's the idea.
Yeah.
That's what you're saying.
So this is mechanical, and an advantage of a mechanical process is that you don't have to think about it. Because you don't have to think about it, you don't get tired. So you can do this for quite a long time and quite fast. And the speed depends only on your skills with using your IDE, knowing your tools and all these things. But from my experience, it goes much faster than the other methods that I tried for legacy code. And now at this point, when you have a bunch of pure functions, you can use data-driven tests, you can use property-based tests, and then just write your tests in a very simple manner. Just generate data, plug into it, see what the result is, and so on. And then move to the last part, which is refactoring to whatever you want to.
So because now you have everything, you understand which are the dependencies and which are the things that you have. So this is basically a way of separating what you have as logic and what is dependency, right? That's the idea.
Exactly. That's the main idea, and I think that's the power of the technique, that without you working too much, or at least without you thinking too much, actually, it just kind of breaks your dependencies into separate things. And by the way, you end up with dependency injection, because passing a function, passing a lambda into a function is basically dependency injection.
It's a kind of a function injection, right? You inject the function instead of injecting an interface or, I don't know, anything else, but it's still a dependency. It doesn't matter which form it is.
And I have to mention here that I often work with programmers that have worked in Java for a long time and just used the framework like Spring and so on. And by dependency injection, they understand, yes, Spring injects dependencies.
Yeah, that's not what it is.
That's not what it is. Dependency injection is a design pattern, and there are at least 4 or 5 different ways to inject dependencies in code, and this is one of them. Spring just does this without you knowing.
It's magic.
It's kind of a magic, which is nice, but it's also...
we need to know what's magic behind anything if you want to understand better what to do.
Right. So the last step is, once you have these pure functions that are separated, how do you move from these to classes?
So you have functions, you have dependencies.
Yeah. And the observation here, which is something I learned through J.B. Rainsberger, although I think it's from a book, but I keep forgetting what book it's from, is that any method that's in a class is actually what's called a partially applied pure function. Basically, what it means is that if you see a lot of pure functions that have the same parameters, those parameters can move in a class's data members. The functions can move there, and instead of using the parameters, can use the data members. And that's how you create a class.
So because they are more cohesive, they belong together because they use the same data. They use the same structures of data, and so it's normal that they belong together in a class. Basically, that's one of the reasons we have classes.
Yeah. And if you want to go into a more functional way, then you turn those parameters into data structures that are more complex. And you keep the pure functions that just receive those data structures and maybe return other data structures or the same, but new values for the same, or things like this. So that's why actually object-oriented and functional design, they are very closely connected. We just need to...
Yeah, I think it's just in our minds that we want to separate them. There are a lot of similarities, there are a lot of differences, but I think if we focus on the similarities, we'll see that we can easily use both of them in our advantage. So I think it's not often the problem, should we program functional or object-oriented? The problem is what's better.
Yeah. So then the only question is, if you have, let's say, functions with more parameters, is like, what does this function fit together with? Because sometimes the decision is not obvious. So, but this is usually a good indication. You have a number of parameters that kind of repeat, and then you look at that and say, okay, so these two functions, they could be together in something named bag, or
you need to give it
something. A name. If you can give it a name, it means that and ideally a name that fits the domain that you work in, then probably you're on the right track towards refactoring into a better design. So that's basically the method.
Okay, and probably we'll follow up with a few code and showing how it's done in a technical approach, in a hands-on approach, right?
Yes, we will do that. I have to prepare a talk anyway for CPP Europe 2020 where I will talk about this. We'll have some examples in C++. I do have a small example in my book on functional programming in C++, but I plan to expand on that. So yeah, it's a very interesting topic, especially since this is a very common problem and very painful and very expensive to solve, actually.
True. Okay, great. So let's see next time how we can do this on a hands-on approach.
Yeah, thank you.
Thank you. See you next time.
Coming next. Today we will look at techniques for refactoring legacy code through pure functions. So what we will look at is one specific idea that I discussed previously in a video with Adrian Bolboaca, which is that we can refactor legacy code by first extracting pure functions through very safe refactorings, then writing the data-driven tests or property-based tests on those pure functions.